Dear friends, here I am going to discuss the laws of reflection on the basis of Fermat's principle. Laws of reflection. We have the reflection is a phenomena in optics that a light ray gets reflected from any smooth surfaces. Let us consider any smooth surface that is any smooth surface AB, and a light ray will incident at point some arbitrary point O in this surface AB, and if this AB is a reflecting surface, this light ray will definitely reflect back to the same incident medium. So discussing about this reflection, the intensity or extent of reflection will depends upon the smoothness of this surface AB. If we are applying or incidenting the light ray to a rough surface, the light ray will get reflect back, but the amount of reflected light ray or intensity of the reflected light ray will be very small. But if this AB surface is very smooth, then the intensity of the reflected light ray will be very high. We are all familiar with smooth reflecting surface such that mirrors and some other spherical reflecting surfaces. In any kind of smooth media, something like a mirror, the intensity or extent of this reflected light ray is almost greater than 90 or 95% of the intensity of the incident light ray. Now, this reflection of this phenomena, the reflection depends on some laws in optics. That laws are called laws of reflection. Now, we are discussing these laws of reflection on the basis of Fermat's principle. Laws of reflection on basis of Fermat's principle. We have already discussed about the Fermat's principle, and we have familiarized the rectilinear propagation of light on the basis of Fermat's principle. That means, according to Fermat's principle, any light ray will choose some specific path for traveling through a medium, and the property of that particular path is the optical path corresponding to the propagation of light ray is minimum. Then that means light ray can choose any arbitrary path, but according to Fermat's principle, this light ray will obey some particular path, and for that particular path, the optical path covered by that light ray will be minimum. Here we are discussing about normal reflecting surfaces, that is some mirrors, and so for the case of normal reflecting surfaces, the Fermat's principle obeys the theory of minimum optical path. Okay, so we are directly entering to the theory. Before that, we have 3 steps for finding the laws of reflection, or applying the Fermat's principle to any laws in optics. First of all, we have to find the optical path followed by that light ray, and in second case we have to minimize this optical path. What I meant is, if a light ray is incidenting from a point some point M, and the reflected light ray is received at point N, then the optical path corresponding to this reflection is MO plus ON. So we will get an optical path corresponding, and let it be capital L. So we are first finding this optical path L, and in the second steps we are applying the Fermat's principle. That means, for that reflecting phenomena, the optical or the correct optical path is the one in which the distance or the geometrical distance, or similarly the optical path is minimum. So we are minimizing the value of optical path with respect to some arbitrary coordinate. If this optical path depends on some arbitrary coordinate, then we will get a new optical path which is the minimum optical path corresponding to this reflection, and that will obeys the Fermat's principle, and that particular the point that corresponding to that particular optical path will be the point of reflection. So in general, first we are considering this point of reflection as an arbitrary point and obtaining the optical path with respect to this the coordinates of this arbitrary reflection point, and minimizes the optical path with respect to general coordinates and finding the minimum optical path, and we can deduce the laws of reflection from this phenomena. Deduce the laws of reflection. Deduce the laws. Okay, now we are going to our reflection phenomena. So here I am denoting a plane that is M1, M2, M3 and M4. This is a point of this is a plane of reflection in a surface, or this is a reflecting surface. This plane of reflection is a reflecting surface. Let us consider for convenience that this plane of reflection is a plane mirror, It is a plane mirror, and we are attaching a coordinate system with respect to this plane mirror. That coordinate system is marked as this one. This is the coordinate system. It is x axis, it is the z axis, this is corresponding to the z axis, and it is the y axis. Okay, now from this figure it is clear that the reflecting surface or mirror is situated at the xz plane. This mirror is in the xz plane, and we are considering an incident point, or the source of light ray is at point A, and this light ray is originating from the point A and reflecting from this reflecting surface M1, M2, M3, M4 some arbitrary point P, and it reflects back to the same medium and it get received at point B. Okay, the originating point is A, reflecting point which is an arbitrary point, it is P, and the receiving end is at point B. Now let us consider this incident point, or the originating point of the light ray is at point A. This point A is situated at the y axis. We are considering this point is situated at the y axis at a distance A, from the origin. So the coordinates of this point A will be 0, A, 0. Point A will have coordinate 0, A, 0. Since it is at y axis and the distance from the origin to the originating point is A from origin through the y axis. So other all coordinate x and z are 0 and the y coordinate will be A. Now we are considering the receiving end, it's at point B, and this point B is also in the xy plane. We are marking this xy plane by the dotted lines. So this xy plane is just perpendicular to the reflecting plane xz. Okay, this M1, M2, M3, M4 plane is the reflecting surface, and we are considering another plane which is just perpendicular to the reflecting plane. So this point B is at the this perpendicular plane, is situated at this perpendicular plane. So this perpendicular plane is nothing but the xy plane with respect to our consideration. So let us consider this B having an x coordinate d, having an x coordinate, that means if I am dropping a perpendicular from this point P to the x axis, this distance, if O is the origin, this OC, distance OC is d, and the distance from the x axis or perpendicular distance from the x axis to the point B is small b, and this point is B, capital B is situated at this xy plane, so its z coordinate will be equal to 0. So the coordinates of B will be d, small b and 0. Now we have another point P, that is the point of reflection, but it is an arbitrary point, so it must have a coordinate x, 0, z. This 0 means that the point of reflection is at xz plane. Now we are going to analyze or obtain the first step, that means we are obtaining the optical path. Now if we are obtaining this optical path, we are imagined some distances a, b, small d, and corresponding to this figure, and we are choosing this point P having coordinate x, 0 and z. That means this point P has x coordinate x and z coordinate z. That means this point P is situated at a point x distance away from the origin through x axis and z distance away from the origin through z axis. So we have some imagined distances here, that is one is a, another is small b and small d, x and z. So we are expressing the optical path in terms of this distance. We have the coordinates in the Cartesian coordinate system, so it is very much easier to obtain the optical path. For convenience, we have optical path is the product of geometrical distance and the refractive index. For convenience, we are choosing the refractive index of medium. Refractive index is equal to 1, that is mu is equal to 1. That means the medium above this plane of reflection is an air medium. Now we are going to obtain the optical path. It is very much easy. That means this optical path is under root x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So this optical path is the geometrical distance itself because the refractive index is 1. Then the geometrical distance is AP plus PB. AP plus PB. L is equal to AP plus PB. That means it is equal to AP, A having coordinate 0, A0 and x, P having coordinate x0, z. That means x minus 0 whole square, that means x square, plus 0 minus a whole square, that means a square, plus z minus 0 whole square, that means z square, plus PB have value x minus d whole square, because b having values d, b and 0, so x minus d whole square plus 0 minus b whole square, it is the b square itself, and z minus 0 whole square is the z square itself. So we are obtained the optical path corresponding to this point of reflection P. Now here this we can see that this optical path depends on an arbitrary coordinate x and z. So according to Fermat's principle, there will not be any change for the point of reflection. That means this point of reflection or the theory of reflection corresponding to a single optical path, that is the minimum value of that optical path. So there will not be any distance or any correspondings or any depends with of the point of reflection or the optical path, or the optical path cannot have any depends with respect to any arbitrary coordinate. That means the point of reflection is a specific one. That means the optical path is the minimum one, that is one and only optical path, and that is the minimum one. There will be a single optical path, so there will be a single point of reflection. So it means there will not be any dependence of this optical path with respect to some arbitrary coordinate. What I meant is, if this point of reflection changing from this x0 and z, that is x and z are any arbitrary coordinate, it can have any values. So if we are changing these values of x and z corresponding to that value change in values, this optical path will be altered. That will not obey the Fermat's principle. Okay, then we have to eliminate this x and z values, or values of x and z, from this optical path. That means the variation corresponding to optical path with respect to x and z will be equal to 0. Variation of optical path with respect to x and z are 0. That means the optical path we have to, according to Fermat principle, the optical path corresponding to the point of reflection is a single one, and that is the minimum one, and the variation from that value of optical path to any other values is greater than 0. Or if we are considering the point of reflection corresponding to the minimum optical path, then corresponding to that optical path the variation with respect to x and z are 0. എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഇവിടെ എക്സ് ആൻഡ് സെഡിന് ഏത് വാല്യൂ സ്വീകരിച്ചു കഴിഞ്ഞാലും കറസ്പോണ്ടിംഗ്ലി ഒപ്റ്റിക്കൽ പാത്ത് മാറുന്ന ഒരു സിറ്റുവേഷനാണ് ഇവിടെ ഉള്ളത്. ബട്ട് നമുക്ക് ആവശ്യമുള്ള ഒപ്റ്റിക്കൽ പാത്ത് എന്ന് പറയുന്നത് റിഫ്ലക്ഷൻ നടക്കുന്ന പോയിന്റിൽ കൂടിയുള്ള ഒപ്റ്റിക്കൽ പാത്താണ്. ആ ഒപ്റ്റിക്കൽ പാത്തിൻ്റെ പ്രത്യേകത എന്താണെന്ന് വെച്ചാൽ ദാറ്റ് ഈസ് ദ മിനിമം വാല്യൂ ഓഫ് ഒപ്റ്റിക്കൽ പാത്ത്. So corresponding to that optical path, variation with respect to x and z will be equal to 0. Now that means variation with respect to x and z are equal to 0 means that dou L divided by dou x and dou L divided by dou z are equal to 0. Now we have to find the dou L divided by dou x and dou L divided by dou z and equating that to 0. First of all, I am finding dou L divided by dou z is equal to 0, which implies L is this value x square plus a square plus z square plus L is this value x square plus a square plus z square plus root of x minus d whole square plus b square plus z square. Then dou L divided by dou z having values 2x divided by 2 into root of x square plus a square plus z square, 2z divided by plus 2z divided by root of x minus d whole square plus b square plus z square into 2. This 2 and 2 get cancelled and you will get is equal to 0. That means z into 1 by root of x square plus a square plus z square plus 1 by root of x minus d whole square plus b square plus z square is equal to 0. That means the quantity inside this square bracket is x square plus a square plus z square whole are squares and added together. This quantity x minus d whole square is also x minus d whole square and b square and z square all are squares and added each other. So there is no possibility that these quantities are being negative. Any one of these quantities are being negative because all are squares, and these two quantities are get added. That means the quantity inside this square bracket will be a positive one. Then z into some positive quantity is equal to 0. This condition is satisfied in a single condition, in a single this z into some positive quantities will be equal to 0 is satisfied at any at a single occasion, that is z is equal to 0. Then if we are applying this value z is equal to 0 to our previous diagram, we will get that the z is equal to 0, then you will get a new point of reflection that having coordinate x, 0 and 0. That means this point of reflection having coordinate x, 0 and 0 means that this point of reflection is shifted to this x axis. So this is our new point of reflection P prime. This is some new point of reflection P prime, and the reflection point is on x axis. So initially this point of reflection will be at a plane, that is at xz plane, and if we are applying or minimizing the values of the optical path with respect to z, then you will get that this point of reflection is restricted to a single line, and that is the x axis. Okay, now point of reflection is shifted to this single point P prime, it is on the x axis. That means here we can see that this initial point A and the point B is already, we have imagined that it is in a plane perpendicular to this point of this plane of reflection. That means these 2 points are in the xy plane, and now we are shifting this point of reflection to the x axis. That means this point of reflection also will be in this xy plane. So according to this reflection law, we are fixing this new ray of reflections like that. This is the reflected ray, and this will be the incident light ray. This will be the incident light ray, and this will be the reflected light ray. And for obtaining the theories of reflection, we have to put a normal at the point of reflection. That means this will be the normal at the point of reflection. This will be the normal to the point of reflection. I am marking it as n. So we can see that the incident light ray and the reflected light ray along with the normal at the point of reflection will situate at the same plane, that is the xy plane here. Okay, this incident light ray and the reflected light ray and also the normal at the point of reflection will be at the same plane. This is the first law of reflection. So from our first observation or first consideration or minimizing the values of optical path with respect to z and equating to 0, we obtain the first law of reflection, that is the incident light ray and the reflected light ray along with the normal at point of reflection is in the same plane, It is the first law of reflection. Now we have obtained the new optical path as root of x square plus a square plus root of x minus d whole square plus b square, that is z is equated to 0, Now this is the new optical path. Here this new optical path also have a dependent in x coordinate, that means x is an arbitrary point. So in our consideration there will not be any dependence of this optical path with respect to x or any other coordinate. So that means now we are chosen the point of reflection in this x axis. That means this point of reflection can vary along this x axis and choose any point along this x axis. For any other points corresponding to this point of reflection, the optical path will also changing. Okay, now we have to restrict this point of reflection to a single point corresponding to minimum optical path. So we have to minimize the value of the optical path with respect to x also. So that means dou L divided by dou X also is equal to 0, implies we will get 2x divided by root of x square plus a square. I am differentiating this optical path with respect to x, that is 2x divided by root of x square plus a square plus 2 into x minus d divided by root of 2x divided by 2 into root of x square plus a square. So 1 by 2 into root of x minus d whole square plus b square into 2 into x minus d and equating to 0. This means that 2 and 2 get cancelled and you will get x divided by root of x square plus a square plus x minus d divided by root of x minus d whole square plus b square is equal to 0. That means x divided by root of x square plus a square is equal to minus of x minus d divided by root of x minus d whole square plus b square. Now this is our observation, that is x divided by root of x square plus a square will be equal to minus of x minus d divided by root of x minus d whole square plus d square. Now we can obtain these values, these geometrical values in our diagram. First of all, x divided by root of x square plus a square, that is this is the value of x and this is the value of a. This is geometrical distance of a. So root of x square plus a square is this hypotenuse. This value of hypotenuse will be root of x square plus a square and it is the value x distance x. So x divided by root of x square plus a square will corresponding to the sine of this angle. That means opposite side divided by hypotenuse. Now if this angle, I am obtaining the sine of this angle through this geometrical method. So if this p dash is a point of reflection and n is the normal at the point of reflection, then this angle will be the incident angle corresponding to the reflection and marking as I. If this is angle of incident I, then this angle also will be angle I. This will also be angle I. That means these two lines are parallel lines and this line is intersecting these two parallel lines. So this and these angles are equal. So root x divided by root of x square plus a square will corresponding to the sine of the angle I. Now the second coordinate is x minus d divided by root of x minus d whole square plus b square. If this is the distance x and this total distance is d, then minus of x minus d will corresponding to d minus x. That means this distance, d minus x is this distance, and root of x minus d whole square plus b square corresponding to this hypotenuse values. So this geometrical distance, ratio of this geometrical distance will corresponding to sine of this angle. If p dash is point of reflection and n is the normal, this angle will be the reflected angle r. If it is reflected angle r, this angle will also be r, because these two are two parallel lines and this line of intersection is cutting these two parallel lines. So this and these angles are equal. So minus of x minus d divided by root of x minus d whole square plus b square corresponding to sine of this angle r. That means from here we can write it as this is sine of I and it is sine of r. That means sine of angle I is equal to sine of angle r. That means I is equal to r. It is the second law of reflection. So from here we are successfully described the theories of reflection and two laws of reflection on the basis of this Fermat principle. That means first of all we obtain the optical path and minimizes its values corresponding to the two arbitrary coordinates x and z and equating to 0, or I am taking the derivative and equated to 0. And first, if I am minimizing with respect to z, I will get the first law of reflection, that is the incident light ray, the reflected light ray, and the normal at point of reflection is situated at the same plane. And if I am minimizing this value with respect to x, I am obtained that this angle of incident corresponding to the for a reflection from any point, the angle of incident will be equal to the angle of reflection. So from our diagram we can see that if this point of reflection is changing along this axis of x axis corresponding to any other values or any other point, this I and R will be changing, and there will be a single point of reflection corresponding to the similar values of incident and reflected angle. So this reflection point of reflection will be a single one, and we are restricting this arbitrary point of reflection to a particular value corresponding to the particular value in the x-axis. The property of that particular point is the incident and the reflected angles are equal. Okay, by this we can conclude the laws of reflection here. Thank you.